There's a limit on how many trials you can run with this program. I forget what it is. It's either 100 or 1,000, which is a big difference. There's a certain number of, well, let's find out. I'll try to run 1,000 and see what happens. 1,000 worked?
No,
Oh, you found it. Good, Haley. Good. I'm just going to try something real quick here. 0, 2. That might fart out right then.
But you have a little line letting you know that it's thinking.
Well, correct, but it will think right up to the time it crashes too. So what I'm waiting to see is if it crashes. If it doesn't crash, that means the list is long. I can't remember how long the lists are. They're finitely long. They're not like an Excel spreadsheet. Well, Excel spreadsheets are also finitely long, but they're pretty ridiculously long. I mean, they're long enough. Yeah, that's exactly what it is. I bet you 100 or 101 is probably about as max as you can do.
Yeah.
But that's okay, because I won't have you using your TI, I won't have you doing any more than,
But
say,
just
50
try
or
100
60 or
just
70.
for us.
So, good. So if we can do 100,
Yeah, that's awesome.
you can do 100, 0 to 100.
Please
And when you
remember.
see it thinking like this,
But right now.
what it's actually doing is, it's filling that L1. 0, 1, 2, 3, 4, 5, 6, and I got a sequence command actually doing that. That's what your TI doesn't have it built in to do automatically, but if you do it in English like this. Okay, so binomial, so now we've got 100 birds in our flock. We've got 100 birds in our flock. It's now filling list 2 with all those problems. Now you got to remember, that first element is you bought 100 birds, and all of them are boys.
Why did you put down 0 now?
0.9.
Why not? Why?
Because it's 90%, still 90% chance of getting a girl on any given trial. Yeah. Now, look at the distribution. Now, this gets a little hard to look at, which would also explain why I gave you another program. So, here's the distribution. Okay, notice it just says 0 in list 1, in list 2. It's not really 0. It's 0.99 zeros and a 1. 0.1 to the 100th power is 0.99 zeros to a 1, but that rounds to 0. But look at these. Very, very small, right? Very, very small. But they're getting bigger. They're getting bigger as you go down. They're getting bigger, getting bigger, getting bigger, getting bigger. And eventually, they actually get kind of likely. But you have to go pretty far. Because right now, for example, this means I got 48 girls and 52 boys. Should that happen? No, there's a 90% rate of females. You shouldn't be getting half and half. That's like flipping a coin. Jade, it's your coin. Except it's not weighted right. This would be if they just took all the birds that were hatched and threw them in a bin and said, go ahead, half price today, because we have no idea what you're getting. Then this would be likely. It would be likely to get 48 and 52. But if they sexed them, they should not be coming in at half and half. So this is all very rare. This is very hard to see. So if you look at I just ran 100. If you look at your program list, you'll see I also gave you one called dist draw. What this does is, if you select dist draw, it gives you a graph of your distribution. It'll actually graph whatever distribution you have in L1 and L2. And that's what it looks like for 100 girls. That's what it looks like for 100 girls. Here's 0. Here's 100. Notice, getting all girls is almost impossible too. But it should make sense. Because if you buy 100 birds, on average, how many girls should you have? 90. You should have 10 boys and 90 girls. So there's almost no chance of getting all girls. The most likely outcome is this guy right here, which is going to be your 90 girls and your 10 boys. And you start seeing a fall. What does that even look like? What does that look like? Oh yes, more on that later, how the bell curve magically appears out of the binomial. We'll come back to that towards the end of class. Maybe, if we have time. If not, that'll be the YouTube video for Monday. So cool. But we didn't have to go to 100, because right now 100 is clearly does the trick in that all girls are not the most likely. Haley, how many did you have to go to?
12.
Look at that. If we go to 12, take a peek. If we go to program, dist fill. If we buy 12 birds, 0 to 12, it's filling 0 to 12 right now. Grab the binomial with probability 0.9, fills it up right there. I'm going to run dist draw real quick. Program dist draw. This just gives us an image of it. And there it is. You see? That's all girls. That's all. Now, the one thing about dist draw that you can do, should you choose to, is you can press the trace button. And then you can skip along it, and it'll actually tell you the random variable value and its probability. So, for example, right here, This is the chance of getting 5 girls out of 12. Now, of course, if you got 5 girls, you also got 7 boys. What's the chance of getting 5 girls and 7 boys? Not very good. Because 5 and 7 is almost 50-50. We're back to Jada's 50-50 coin. But it's not 50-50, it's 90-10. Anthony, please.
I got that differently on 9 or on 10.
Good. We'll come back to that too. I was 12 surprised me. I'm glad we used 12 though. So now you can go over to. Where's my spider? There he is. Now we're starting to get into the world of the likelihoods. Likelihood, boom. There it is, there it is, there it is. Boom. 11 girls and 1 boy. It's the most likely, but look at how small that is compared to when you buy fewer birds, right? I bought 4 birds. It was like 66% likely that they were all girls. Now this is the most likely outcome, but it's only at like 38%. But it has to be like that, doesn't it? There are so many options to choose from now. With 4 birds, there's only 5 options, 0 through 4. With 12, there are 13, 0 through 12. So that has to spread itself out. There's still going to be a most common outcome, but there's also going to be many, many more lesser common outcomes. So Anthony, you ran 10. Let's do that. Let's run disc fill on 10 birds. Nice metric flock. Nice metric flock. Binomial. 0.9. There she comes. We can take a look at it if you'd like. I like disc draw. It gives you a nice visual. Look at that. 10 does it. Now 10, hopefully it makes sense that 10 does it. Because 90% of the flock should be female. 90% of the flock should be female. So if you buy 10, it would be 9 and 1 on average. You'd get 9 and 1. 9 out of 10 is the same average as we get for a flock of 1. 0.9 out of 1. It's all the same ratio, right? It's all the same ratio. Does that make sense? So eventually there comes a point when even when you have a highly skewed binomial distribution like this one, eventually it will start peaking and then moving towards the center and you get that beautiful bell curve. Like I said, more on that momentarily. We'll get to that momentarily. Jada, go ahead.
So if you buy your birds separately, like one at a time, then but you still have 4 or whatever, that it's like 90% chance.
If, assuming that the same proportion is in effect at the store at all times, yes, there should be, you're probably actually closer to a true binomial then, because you're not removing as large a chunk of the population each time. Assuming they're replenishing the birds that you buy.
Yeah.
Assuming that, you're actually more independent than than you're doing it this way. But yeah, assuming, and this is a big assumption, and this is what 244 is all about. Because for example, I once had a friend who bought 25 birds from a supplier who said there's a 90% identification rate. He bought 25 birds and they were all girls. Now what's the chance of that happening? Oh, we can figure it out now, can't we? Yeah. We can figure that out. If he bought 25 birds, the least number of girls he can have is 0, and the most is 25, which is what he got. He got 25, correct? Okay. Fill it with binomial at a 0.9. Here she comes.
I also bought some.
I'm gonna graph it, okay? If it's okay with you guys. This is because there's 26 spots. It's hard to see in the table. Possible, but not as probable as fewer, correct? So if you trace it, can I go backwards and trace? I can't. I have to go all the way over. So let's put 25 in. Oh, they won't let me do that. You son of a. Got an arrow over to 25. The chance of it happening is about 7%, which is not considered unusual by the outlier cutoff, but still, that's pretty small. I mean, you're more likely to get a couple boys in that mix because the binomial says out of every 10 birds that you buy, one's going to be a boy. So if you buy 25, you should essentially have 2.5 boys on average, right? On average, 2.5 boys, which means you have 22.5 girls. 22.5 rounds to 23. So you should have had 23 and a couple boys mixed in there, but he didn't. He had all girls, which is fairly rare, And that's the idea of this. It actually allows you to analyze. So I look at that and I say, I wonder if they're actually, and this is a good 244 question, are they actually sexing these pullets at a higher rate than 90% correct? This might imply yes, maybe they are. I'd like to see a bigger sample. It's not quite, 7% is still high enough to push it into that greater than 5% range. So I'd like to see a couple hundred trials. How do we get for a couple hundred trials? A couple hundred trials coming in. Out of 100 like we did earlier. Because once you get to 100 birds, there's almost no chance they're all
Our
girls.
maximum.
Assuming they're using a 0.9. Now, suppose they're going at a 0.95 success rate. Yeah, watch this. Watch this. Suppose we do the exact same question. Whoops. That 25 shouldn't be there. Suppose we buy 100 birds. It'll take a couple seconds. But they're not accurate to 90% anymore. They're accurate to like 95%. Okay, 0.95. All right, so not 90, but 0.95. Okay, let's take a couple seconds. And then graph it when you're done. Okay. How does that look different than when they were at 90%? Do you remember?
Yes.
Right? The difference was the 90% curve was over here. The most likely outcome was 90 out of 100. Now it's 95 out of 100. So there's 95, 96, 97, 98, 99, and 100 right down there.
Yes, this is nice.
So they are higher than they were before. They're not as close to zero. They're still rare. Because if you buy 95 birds, you should be getting 9.5 girls per 10, 0.5 boys per 10. So that ends up being 5 roosters on average, which, again, is indicated right there. That's the most likely outcome. Fair enough? You guys buy what's going on? Cool?
The suppliers usually they at minimum 25 birds because of the
Gotcha.
shipping and stuff, but
Sure.
probably this also. But they usually give you 2-3 birds just in case.
Just in case, just to make up for the roosters you're going to get. Because say out of 25, you expect 2 roosters. So here's 2 or 3 birds to hopefully, not with 90% each, that you're looking at 2 or 3 extra girls. Because in 3 birds from yesterday, there's about a 73% chance they're all girls. That's pretty good. 73% is all good. So here's your 25 plus 3 extras just to make more poop in your car on the way home. And therefore you're raising the likelihood that you've got at least. So that's another good question, which we'll save for another time, but how many birds would you have to buy to make sure you average a certain number of females? And again, it's a great question which we'll get around to as we go through the day. I mean, that's one of those many good questions.
Out of 3 trials, they had only one particular flock which had a rooster.
Out of 3?
3 trials, 25 each. One time I bought actually 50 birds.
Uh-huh.
They gave me more. I had only 1 trial with 1 rooster.
Well,
That's
yeah,
it.
but then you question his 90%. That's data that doesn't support 90%. It actually supports a higher than 90%.
Yeah.
And that's,
Yeah.
that's the beauty of statistics is
It
you can
is
put a
cool.
you put a number on that and say, you know what, I think you're doing a better job than 90% accuracy. But that's the number I'm always given when I go to the stores.
No.
So what I want to do now is I want to make sure that that's Mike. He has chickens too. I used him last term. I'm going to give you some experiments that have distributions attached to them. And I want you guys to decide if they're binomial or not. Because now you know what a binomial experiment looks like. It looks like chickens. But that's not the only kind of binomial experiments. There are other ones too. But the trick is being able to identify whether something's binomial or not. So here, you're going to roll a single die like we did in class. And you count how many pips, how many numbers show up on the top face. Is that binomial? Why is that not binomial? Because there are 6 outcomes. There are 6 outcomes. It's multinomial, not binomial. It's multinomial. So that doesn't satisfy the first part of the definition of binomial. Go, Jada.
But what if you said, like, okay, roll the dice and you could get a 2 or a 3?
Like that.
Yeah.
Yes, my friend. Nice. You can make it binomial. Thank you for the segue. That was perfect. Checks in the mail. Yes. Then you can make rolling a single die binomial if you're betting on a single number. Or say on 2 numbers. You might say I bet on 2 or 3.
Yeah.
Well, then the binomial would be either getting a 2 or 3 or not getting a 2 or 3. Either getting a 3 or not getting a 3. So yes, you can definitely make it binomial. But if your variable is the number of pips that you get, that can't be. But that for sure is. That for sure is. Oh, nice, my friend. Very nice, very nice. Let's stay with the dice for a second here. Oops, there we go. Rolling 2 dice and adding up the pips that you get, like you did in class. Binomial. No, there were 11 outcomes. Snake eyes, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 11 different outcomes. So again, it's a multinomial experiment. It's a multinomial experiment. But how about this? Throw a pair of dice and bet on 7 or 11. Well, you're either going to get 7 or 11, or you're not going to get 7 or 11. That becomes binomial. Is that fair? Is that fair?
Yeah.
Now, we haven't been checking the other things. All we've been checking right now is the bi part of the binomial. We haven't been checking the independent trials. And there's not much to talk about. We're rolling 2 dice one time. Both dice are independent of each other. Even the single die, you're just rolling a single die. So let me make it more interesting here. Suppose you roll 2 dice 5 times, and you bet on 7 or 11 each time. Is that binomial? What do you think? What's your gut tell you there? Think about that. Kind of like playing Chuck-a-Luck, except you're only using 2 dice instead of 3.
Yeah, but again.
What do you think? Think binomial?
Either you have them or not.
Good.
Binomial.
So that's the bi part. You either have 7 or 11 or you don't.
Yeah.
Do you have a fixed number of trials? 5. Are they independent trials? If the dice are working, they are, right? So could we model this distribution in your TI? Yes. Let's do it. Let's do it. Switch over to the doc cam. Grab your TI. Let's model this experiment. All right? Let's model it. So fire them up. Let's go to your program, dist fill. So remember, the fixed number of trials. How many times do we play this game? 5. What's the least number of times you could get 7 or 11?
0.
You might never get 7 or 11, correct? 0. What's the most number of times you can get 7 or 11?
5.
All 5, right? You could get it all 5 times. So the least number is 0, highest number is 5. So once again, this is buying chickens. But the coin, which has 2 sides, is not 90-10 or 50-50. The question is, what is the coin weighted? How is the coin weighted? Well, that's what you have to put in here. The binomial. How is the coin weighted? Think back to last week or the week before, and that's okay if you don't remember. You have to roll a 7 or an 11. Remember how many ways you can do that? Do you remember? Did any of those numbers pop back into your mind from, it's okay if they don't. There's a 6 in 36 chance of getting a 7, and there's only 2 ways to get an 11. 5, 6, 6, and 5. So there's 8 total ways out of 36. That's the chance. 8 in 36 is the chance of getting 7 or 11. 8 in 36.
Okay.
Right? So you can put that in. 8 divided by 36. That's your weight on the one side. No longer is it 90-10. It's now 8/36 and whatever's left over.
So we can actually do that like...
Oh, hell yeah, the TI smart enough to calculate it.
Okay.
She's done. Let's take a look at it. There's your distribution, friends. What's the most likely outcome out of 5? What's the most likely outcome out of 5? Mimi says 1, and there it is. You're most likely, if you throw the dice 5 times like this, you're most likely going to get 1, 7, or 11 out of those 5 trials. Are you likely to hit all 5? 4 out of 5? 3 out of 5? Starting to go up now. Creeping up. 2 out of the 5 and none out of the 5. None of the 5 is actually pretty likely too, isn't it? What's the likelihood on that one? That one is at 28%. Yeesh. That's like 3 in 10 trials. There's 3 in 10. Fair enough? And what is the beauty of having the distribution in L1 and L2 now? What can you do with it? Once it's in L1 and L2. You can graph it, clearly. But what else can you do with it? You can find the average. Now, what we're doing right here, Mimi, you got to be the mode. The most likely outcome is the mode, for sure. Highest part of the graph, just like it always has been. But now you can also go for the long run average, which might not, generally, it's not exactly equal to the mode. So let's go ahead and do that. Let's do a little 1-bar stats on L1 and L2. There you go. It's just a little bit higher than 1. A little bit higher than 1, because the tail's pulling it. It has outliers, correct? The distribution has outliers to the right, and the average is pulling a little bit to that side. And the more extreme the distribution, the more the outliers will pull. Fair enough? Yeah, ish. See how it's tying and everything else we did before? Kind of tying there. Good. Yeah? All right. Let's back to the critical thinking, deciding whether something's binomial or not. All right. Now I want to move away from dice. Forget this. Yeah, here we go. Here's a good one. Get a little 244 on you here. What you thinking about 244? What do you think? What do you think? Binomial?
They either have it or they don't.
They either have it or they don't. It's bi, for sure. It's binomial. Independent trials?
20 random.
I'm picking 20 guys out. Isn't that changing isn't that changing the percentages of the guys in America? It is, literally, but essentially, is it? No, how many guys are in America? Ish.
150.
150 million? You're pulling 20? Are we changing anything? No, we're pulling chicks out of these bins at this point, right? You're pulling a chick out of a bin. So arguably independent trials, definitely binomial. Fixed number of trials? Selecting 20. Boom, 20 is your... Can we model this in our TI?
Yeah.
Hell yeah, we could. Let's model it. Let's model it. Our flock, it now has 20 birds in it. Everything's a chicken, friends. If it's binomial, it's a chicken. It's chicken, it's a rooster, it's 90-10. But it's not 90-10, it's 793 in this one, isn't it? Because 7% have color blindness. So we go program, just fill. Okay, the smallest number of guys that can have color blindness is? 0, none. The largest number is? 20. Beautiful. There we go. It's binomial for sure. The chance of color blindness?
0.07.
0.07. Make sure you put the 0 in there. Otherwise, you're going to say 70%. Ooh, like I just did. Otherwise, you're going to say that 70% of guys have colorblind. Slightly different. Slightly different. Let it think a couple seconds. Let it think a couple seconds. Let's take a look at it. Yeah, there she is. It looks like the chicken curve, except it's over there instead of over here. But hopefully that makes sense. Why is it over here versus over here? Because the chance of success is low. It's 7% versus 90%. If you did the number of guys that don't have color blindness, it would be over here. I can't turn it upside down. I wish I could. Well, you just rerun it again with 93% if you wanted to. That would give you the exact same result. Cool? Definitely binomial. Fixed number of trials, independent results, constant probability of 7%. Love it. Love it. Love it. Is TI feeling better to you guys now? You started to like, okay, I got this now. Good. Let's try this one. Wait. There we go. I did. It did. No, it's not. Read it. That's why I had to look at it. It changed so quickly I didn't notice. Let's go through our checklist. Let's go through our checklist. So 7% of men, and this first sentence is identical. It is. It is identical. You keep selecting men at random until you found 20 that have RGCB. Okay, so is it bi? There's the two outcomes.
Yeah.
They either have it or don't.
Yeah.
As you select men out of the independent, because I mean you're grabbing guys.
Yeah.
But then,
Sit, Jada.
but then you like throwing them back if they, but
Assume you. That's a great question, and it sometimes it doesn't. Jada's question is: are you throwing them back in if they don't? My problem is this.
Keep
What do we break? We broke a requirement of the binary. Fixed number of trials. This is a non-fixed number of trials. This is not binomial. This is actually called the geometric distribution. Keep doing something until you get a desired result. That's different than a binomial, which is here's a fixed number of trials. Did you get the result? That's the difference. This is called a geometric. Don't memorize that. That's not important to know. You can look at the video later if you want. This is not binomial, so therefore we cannot model it. What would you put into your TI? Right? 0 to how many would you have to select? You have no idea how many you have to select, right? It's a different input system, which I didn't give you a code for because I didn't want you to have to code that. Fair enough?
So it's the whole population. So.
Essentially, there is a likelihood that you'd have to actually grab a significant chunk of guys to get 20 if only 7% of the guys have it. And at that point, it goes back to Jada's question that have we selected so many that we're actually changing the underlying population? Probably not for guys and American men, but overall, check this out. Here we go. Here we go. They all start the same, these lists right here. They all start the same. Now, there are only 10 guys in the class to select. Most of my classes have at least 10 guys in them. So let's just say there was a class of 35 here, which is my, let's be realistic, 45. Most of my classes are around 40, 45. All right? And they're usually half guys, half girls.
So this is binomial because we've got this 10 people.
So I'm fixing it at 10 people, right?
They
Fixing it
do
at 10.
have it or not,
They either have it or don't, but
but
think about what I said. My class is, let's make that number easy. My class has 40 people in it. Half are guys, half are girls. I'm going to draw 10 from the guys. What's the problem, Jenny?
What?
What's the problem with drawing 10 guys when there are 20 in the class? Think back to what Jen said about...
They will be all of them. You don't randomly choose.
Well, I can make sure, I could do that. That's a good point. I could do that using technology, set up a random number generator,
Okay.
and use a shuffle. I could actually take my iPod down to 20 songs on and give each guy a song. And when I shuffle it, when that song comes up, you're picked, and I select you. I could do that. That'd be kind of fun, actually. We'll do that at 2:44. But
It will be not.
this is not by me.
Still 50% of the population.
Right. The problem is I'm drawing too many from this very small population. This is like Max going into the store and drawing 4 birds, but there's only like 6 in the store. You can't assume it's 90% each time anymore,
Yeah.
right? You can't assume that. Let's make the math easy. Max goes into the store. Max goes into the store and buys. And we can't do it with 4 because the math doesn't work out. Let's make it. Let's say he has to grab. There's 10. There's 10 in the store. He goes in to grab birds out. The first one he grabs has a 90% chance of being a girl because 9 of the 10 should be girls. But now there's 8 out of 9 girls left, right? Now we're down to like 88%. Then he grabs one of those girls out. Now there's 7 out of, or whatever amount to, 7 out of